Okay, so let's continue our discussion on group analysis. In the previous lecture, as far as I remember, we had discussed two specific groups. One was, I guess, group of order 30, and one was a group of order PQ, such that P is less than Q and P does not divide Q minus 1, right? Okay. In this lecture, we are going to cover three important groups. One is a group of order 12. In this case, we tend to show that either G has a normal silo 3 subgroup, or G is isomorphic to A4, and in that case, it has a normal silo 2 subgroup. Okay. Number 4, we are going to discuss groups of order P square Q, where P and Q are both primes, are distinct primes precisely. And in this case, we aim to show that it has a normal silo subgroup. It can be a silo P subgroup or can be a silo Q subgroup. It has a normal silo subgroup. Our fifth group analysis will be groups of order 60. A group of order 60, and in this case we show that if G has more than one silo 5 subgroup, then G is simple. That is, G has no non-trivial normal subgroup. But for these three group analyses, these two group analyses are essentially required. So please go and have a look in the previous lecture and then come to this lecture. Then you will have a better understanding of what I'm going to say throughout. Okay. So let's start with a group of order 12. Okay. So number 3. The obvious procedure which we would want to follow is that we would assume that there is no unique silo 3 subgroup. And in that case, we show that G is isomorphic to A4. Most of our proofs will be quite combinatorial. That is, we are gonna check, have a essential checking of the number of elements to be precise of the fact about uniqueness of groups. Okay. So let's start with a group of order 12. Suppose I will be as informative as possible. I'll try to explain each and every step till possible. Okay. Suppose so we are using the notations as used in the as fixed in the previous lecture. So that is one more reason you should have go and have a look at the previous lecture. Suppose G is a group of order 12. Suppose G is a group of order 12. Let N3 be not equal to 1, where N3 represents the number of silo 3 subgroups in G. Let P be a silo 3 subgroup of G. Let P be a silo 3 subgroup of G. Okay. Now, what are the essential informations we have? First thing we have is that, which we obviously are going to use here, that N3 must divide 4. Because see, 12 has a prime factorization of 2 square 3. So obviously N3 will divide this element 2 square. If you recall that if you have a group of order P square, P to the power alpha M, then a silo, the order of the number of silo P subgroups will divide this element M, where P and M are co-prime. These things are covered in the previous lecture. So N3 must divide 4, and N3 has the it has the form 1 plus K3, where K is some non-negative integer. So let me just write N union C. Okay, these come from the Silo third theorem precisely, but the only possibility when N3 is not equal to 1, N3 to divide 4 and N3 to be of the form 1 plus K3 is that K equals to 1, or N3 is precisely 4. Okay. Now Silo 3 subgroup, each Silo 3 subgroup has three non-identity elements. Four non-identity elements. Has two non-identity elements, and distinct Silo 3 subgroups will intersect at identity. Okay, will intersect at identity. But then what are the total number of elements of order 3? That implies there exists exactly 8 non-identity elements of order 3, because we have 4 Silo 3 subgroups, and each of these 4 subgroups contain 2 non-identity elements, and order of these 2 non-identity elements is 3. So we have 4 times 2, 8 non-identity elements of order 3. Okay. So this is something which we would require, obviously. Now, recall this was also a part of the Silo third theorem, that NP, that is number of Silo P subgroups, is the index of the normalizer of an arbitrary Silo P subgroup in G. Now N3, so it will be G, the normalizer of P in G, where P was chosen to be some Silo 3 subgroup. Now N3 has value 4, G has value 12, and the index of the normalizer of P in G by Lagrange's theorem is nothing but order of G by order of the normalizer of P. But since this equals N3, so it must be equal to 4. Now this has value 12, then what is the only possibility for the normalizer of P in G, the order of the normalizer of P in G? So it must be 3. Now order of P is also 3, right? Now, by definition of a normalizer, P is contained in the normalizer of itself, but both are having same order, but order of P is same as 3 because it's a Silo 3 subgroup, which is same as the order of the normalizer of P in G. But that implies P must equal the normalizer of P in G. Clear? Okay. Now what we try to do is that we make G act on the 4 Silo 3 subgroups. Let G act on the 4 Silo 3 subgroups. Okay. Or you can think of G acting on this Silo 3G, sorry, the collection of all Silo 3 subgroups in G. Okay. Now recall that when we have studied group actions, we had said that if G acts on A, then this precisely, it induces a mapping, which we can say as sigma G of A getting mapped to G dot A, where this is precisely the action of each element of G on each element of A. But since this action is a mapping from A to itself, so this sigma G is a mapping from capital A to itself. Hence, actually it is a permutation, because you choose an element small g from capital G, and this small g acts on small a to give another element of small a. So indeed it's simply a permutation of the elements of A. So therefore, this sigma G indeed induces another mapping on G to SA, where SA represents the collection of all permutations of the elements in A, which is obviously a permutation group, such that phi of G is mapped to sigma G. So precisely, given a permutation, it induces a mapping from G to the permutation group of the elements in the set on which G is acting. So if I make use of this fact, let's go to the next page. If I make use of this fact here, so we are making G act on the 4 silo 3 subgroups, and we precisely make this action by conjugation. So let G act on the 4 silo 3 subgroups by conjugation. By conjugation, right? But then what happens by definition? Then this affords permutation representation. Permutation representation is basically the mapping phi, which is induced by the function sigma g, where sigma g is induced by the action. Then this affords a permutation representation phi from G to S4, because there are 4 elements in silo 3G. That is, there are 4 distinct silo 3 subgroups. But there's a very important fact about this permutation representation, that this phi will send each element of G to sigma G. And what does sigma G does? Sigma G of each silo 3 subgroup will send it to its conjugate, right? But therefore, what does kernel of phi does? So kernel of phi will consist of those elements in G which gets mapped to identity in S4. So G gets mapped to the identity permutation in S4. But then that means that the elements in the kernel will typically normalize A, normalize each element A. It will fix on each element A under conjugation, because sigma G becomes the identity map, right? Therefore, this kernel phi will normalize all silo 3 subgroups, right? The kernel of phi is a subgroup of G which normalizes all silo 3 subgroups, right? It normalizes all silo 3 subgroups. That is, if you pick out an element from kernel of phi, then the conjugation of each element of silo, each silo 3 subgroup will get fixed under conjugation by these elements in kernel of phi. That is what I want to say. But if it normalizes all silo 3 subgroups and P was assumed to be a silo 3 subgroup, then this implies, by definition of some set normalizing some other set, that is, kernel of phi must be in the normalizer of P. But normalizer of P is exactly P. But now this happens for all P in the silo 3 subgroup, collection of all silo 3 subgroups, right? Because P was arbitrarily chosen. But all, but P is not normal, right? Assumably, P is not normal, which implies that since this kernel of phi is present in every silo 3 subgroup of G, therefore it must be present in the intersection of the silo P subgroups from G. And since P is not normal, so P is not unique, there are distinct silo 3 subgroups. Hence, we can say that kernel of phi is in the intersection of all the silo 3 subgroups. But all distinct silo 3 subgroups must intersect in identity. Therefore, kernel of phi must be identity. But that we know that if kernel of phi is identity, then phi is a homomorphism. So phi is 1, 1. But therefore, by first isomorphism theorem, now see, this phi is a homomorphism. This phi is indeed a homomorphism. It's evidently a homomorphism. So by first isomorphism theorem, we know that G mod kernel of phi must be isomorphic to the image of G under phi. But kernel of phi is coming out to be just 1. So we have G isomorphic to phi of G. But by due to isomorphism, this phi of G is indeed not due to isomorphism, due to homomorphism. Image of a group under homomorphism is a subgroup of the codomain group. So G is isomorphic to its image under phi, and this phi of G is isomorphic, is a subgroup of S4. That's precisely what we have. Now we know that under isomorphisms, number of elements of the same orders get preserved, right? Because isomorphism typically means that the group structure is same. So if there are n groups of order m in some group, then its isomorphic group will also have n elements of order m. In other words, since G has 8 non-identity elements of order 3, so does phi of G. But phi of G is a subgroup of S4, hence so does S4. But all these elements, that is all these 8 non-identity elements of order 3, but all these elements are in A4, But therefore, we have a non-empty intersection between phi of G, which is a subgroup of S4 containing all the 8 non-identity elements, and these all 8 non-identity elements by the structure of A4 are contained in it. Therefore, the intersection of phi G and A4, this must have order at least 8, right? This must have order at least 8. Therefore, if it has order at least 8, now we know that by Lagrange's theorem, the order of a subgroup must divide the order of the group. So, the order of phi G intersection A4 must be such that it divides both the order of phi G as well as the order of A4, right? But order of A4 is 12. Obviously, order of A4 is 12. Order of phi G is also 12 because G has order 12 and G is isomorphic to phi G. Therefore, the only possible order of phi G intersection A4 must be 12, which implies the order of phi G intersection A4 is 12. But if so, now since phi G intersection A4 is contained in both phi G and A4, and both phi G and A4 has order 12, therefore phi G must equal A4, right? And this means that G is isomorphic to A4. So first part of the claim is done. We are only left with the second part of the claim, that if G is isomorphic to A4, then it has a unique silo 2 subgroup. But that's quite evident. The reason being, see, A4 already has 8 non-identity elements of order 3. Now, obviously, A4 will have a silo 2 subgroup, and this silo 2 subgroup will be of order 4 because the prime factorization of 12 is 2 squared times 3, right? Therefore, rest of the elements are contained in the silo 2 subgroup, which surely exists and has order 4, and no element of order 3 can be there. So are contained in the silo 2 subgroup, and hence only one silo 2 subgroup is possible. Only one silo 2 subgroup is possible, right? So if you have a unique silo 2 subgroup, indeed it must be unique, right? Or normal, whatever you want to say. Got it? Okay. Now let's talk about groups of order p squared q. Now this is a simpler case. So this is the number 4, right? So let G be a group of order p squared q. Let G be a group of order p squared q where p and q are distinct primes. Where p and q are distinct primes. Okay. Distinct primes. Now, so suppose p is greater than q. Now we know that np must divide q, and np precisely has the form 1 plus kp, where k is obviously a positive integer, or I mean a non-negative integer. But since p is greater than q, the only possibility for a number of the form 1 plus kp to divide q is that k is equals to 0, or np is equals to 1, but that means capital P must be normal in G for the capital P being a silo P subgroup of G. One second. Clear? Okay. So the case P greater than Q is trivial, right? Because if the prime P is greater than Q, then surely the silo P subgroup will be normal in G, right? So let P be less than Q. If NQ is equals to 1, then it's trivial again, because if NQ is equals to 1, then the silo Q subgroup is normal in G. So obviously, let NQ be not equal to 1. Okay. So let's go to the next page. Now we know that NQ must be of the form 1 plus KQ, where K is some positive non-negative integer, and 1 plus KQ, that is NQ, must divide P square. Okay. So if 1 plus KQ divides, if 1 plus KQ divides P square, then that implies that KQ divides. So in other words, I can say this as am I doing it right? Yeah, so NQ, sorry. Yeah, NQ must divide P squared, correct? NQ must divide P squared. If NQ divides P squared, then P square, so this implies, what can I say about the divisibility of P square by Q? That is what I want to ask. See, observe the fact that if NQ divides P squared, then NQ must be equals to P or P squared, correct? If NQ divides P squared, then either NQ must be P or P squared, because we have assumed that NQ is greater than 1, right? Now, NQ cannot be equal to P, as Q is greater than P, which obviously implies 1 plus KQ, which is equals to NQ, is also greater than P. So this is obviously not the case. Therefore, NQ must be equals to P square. But if NQ equals to P square, that obviously means that KQ must divide P square minus 1, right? Because if NQ equal to P square, that means 1 plus KQ equals to P square, but that means KQ divides P square minus 1. But P square minus 1 is nothing but P minus 1 times P plus 1. So in other words, sorry, I am writing it wrong. KQ equals to P square minus 1. But this implies KQ equals to P minus 1 times P plus 1. But that means Q divides P minus 1 times P plus 1. Correct. I stated it wrong, because 1 plus KQ equals to P square in this case. 1 plus KQ equals to P square in this case. So KQ must be equal to P square minus 1, but that implies Q divides P square minus 1, which implies Q divides P minus 1 times P plus 1. Now, since Q is prime, and we know that from the properties of prime, Q either divides P minus 1 or divides P plus 1. Now, surely Q cannot divide P minus 1, because Q is greater than P. Q is greater than P. So since Q is greater than P, Q cannot divide P minus 1, right? Therefore, Q divides P plus 1. But since Q is greater than P, and we are talking about integers here, so the only possibility for Q to divide P plus 1, so Q divides P plus 1 if Q equals P plus 1, right? But then Q is prime. So we have here consecutive primes. Since Q is prime, we have Q and P being consecutive primes. Q and P being consecutive primes, where P is less than Q. But the only consecutive primes which we know are P equals 2, and if P equals 2, then Q equals 3. But that implies the order of G must be 12. And we know from the group analysis of a group of order 12 that it either has a silo 3 subgroup, or it has a, sorry, it either has a normal silo 3 subgroup or it has a normal silo 2 subgroup, right? So from here, you know, it can be just analyzed from the analysis of groups of order 12, right? Correct? Okay. One second. Okay. So now we are left with only one more group analysis, which is groups of order 60, number 5, I guess. Okay. So what we try to prove is that if the a group of order 60 has more than one silo 5 subgroup, then it needs to be simple. That is, it has no non-trivial normal subgroup. So let G be a group of order 60. So now 60 has a prime factorization of 2 square times 3 times 5. So it indeed has a silo 2 subgroup, a silo 3 subgroup, and a silo 5 subgroup. At least a silo 2 subgroup, a silo 3 subgroup, and a silo 5 subgroup. What we do is we proceed by contradiction. We proceed by contradiction. We start our analysis under the hypothesis that even if G has more than one silo 5 subgroup, it still has a non-trivial normal subgroup. That is, let G has G has more than one silo 5 subgroup. We assume there exists some H in G which is normal, such that H is neither equal to the trivial subgroup, trivial identity subgroup, or G. Okay, so we will reach some point of contradiction to this assumption, and that will be the end of the proof, obviously. Okay, observe that. So we have assumed that n5 is greater than 1. Now, by the silo third theorem, n5 must divide 12, that is 2 squared 3. But n5 is of the form 1 plus k5, where k is a non-negative integer. So this must divide 12. But observe that the only possibility for this to divide 12 is k must be equals to 1. That is, n5 must be equals to 6. Right? Right. Now let P be a silo 5 subgroup. Let P be a silo 5 subgroup of G. Now we know from silo third theorem that NP, that is number of silo P subgroups, is equal to the index of the normalizer of a silo P subgroup in G. So this implies N5 is the index of this silo 5 subgroup under in G, but N5 is what did we get? 6, right? N5 is 6. Order of G is 60. Now this index is order of G by order of the normalizer of P in G. So we have 6 equals to 60 divided by something, so that something must be 10. So order of the normalizer of P in G must be precisely equal to 10. Right? Okay. Now, suppose H is normal in G. Okay, suppose H is normal in G. And H is that subgroup which is a non-trivial normal subgroup. So it's the non-trivial normal subgroup we are speaking about. Okay. Suppose 5 divides the order of H. Then by the silo theorems, this implies H has a silo 5 subgroup. Right. Now we know that silo P subgroups are mutually conjugates, right? We know that if P and Q are silo some small P subgroups in G, then P and Q are conjugates, right? We have assumed that the silo 5 subgroups are not unique. That is, there are more than one silo 5 subgroup, and each of these silo 5 subgroups are mutually conjugates. But what the observation does this immediately give? Since H is normal, and H has a silo 5 subgroup, and suppose since H has a silo 5 subgroup, suppose P is in H indeed, because we had assumed P to be a silo 5 subgroup. Then all the conjugates of P are also in H. Then all the conjugates of P are also in H, because H is normal. But this implies that H contains all the silo 5 subgroups. H contains all silo 5 subgroups, right? Because every silo 5 subgroups are mutually conjugates. So they are conjugates of P, right? So H contains all silo 5 subgroups. Okay, so this is a very important observation. We will see it now. Why is it so? Now, each silo 5 subgroup, observe that each silo 5 subgroup has 4 non-identity elements, and all of them intersect in identity. All of them intersect in identity. There are 6 silo 5 subgroups. So the order of H, therefore order of H must be greater than or equal to the identity element. So the one element, the count of 1 comes from the identity element, plus the number of total non-identity elements which come from the silo 5 subgroup. So there are 6 silo 5 subgroups, and each of these silo 5 subgroups contain 4 non-identity elements. So that is precisely 25. But order of H must divide order of G, which is 60. And the only factor of 60 which is greater than or equal to 25 is 30. So this immediately implies that order of H is 30. Now recall from the group analysis of the groups of order 30 that each group of order 30 has a unique or a normal silo 5 subgroup. But each group of order 30 has a unique silo 5 subgroup, which is obviously not the case here because H has 6 silo 5 subgroups, right? Contradicting the fact H has 6 distinct silo 5 subgroups, right? Therefore, H cannot be normal in G when it's non-trivial, right? So if we consider a non-trivial subgroup in a group of order 60, then 5 cannot be a factor of its order. But what are the only possible orders of H then, right? Therefore, the order of H can be 6 or 12 precisely, right? Now observe that if order of H is 12, then we know that H will be isomorphic to A4, and in this case it will have a normal silo 5 subgroup, sorry, normal silo 2 subgroup, and else H has a normal silo 3 subgroup, right? This comes from the group analysis of groups of order 12. So it has a normal silo 3 subgroup, right? If H is of order 6, then observe that suppose the number of, so 6 has a prime factorization of 2 times 3. So it obviously has a silo 2 subgroup and a silo 3 subgroup. Suppose the number of silo 2 subgroups in H is greater than 1. But N2 has the form 1 plus K2 and it must divide 3. But that implies the only possibility of N2 can be 3. But if we consider that the number of silo 2 subgroups in a group of order 6 is 3, Each subgroup contributes one non-identity element, and each of these three silo 2 subgroups will intersect in identity. Therefore, the total number of elements which comes out from these three silo 2 subgroups are so we have one from each, and then so it's four, right? One non-identity element from each of them and the identity element. So we have four of them. But what are the number of elements left in a group of order six? So we are only left with two elements, right? So considering these two elements plus the identity element, we get the silo 3 subgroup because it will surely exist. But the only possibility for a silo 3 subgroup is that it needs to be unique because it has exactly three elements to consider, right? Therefore, if n2 is not equal to 1, then we have a unique silo 3 subgroup, else it will have a unique silo 2 subgroup. So what do we conclude from here is that, therefore, if the order of H is 6 or 12, then H has a normal silo subgroup. So it always has a normal silo subgroup, be it a silo 2 subgroup or a silo 3 subgroup. Hence, a characteristic subgroup. Hence, a characteristic silo subgroup. Because recall that unique subgroups are characteristic subgroups. So if H has a normal silo subgroup, then it means that H has a unique silo subgroup, but a unique silo subgroup needs to be a characteristic of H, right? Now, if P is the unique silo subgroup of H, then we have that P is a characteristic of H. H is normal in G by assumption, but we know that if P is a characteristic of H and H is normal in G, then P is normal in G as well. The characteristic subgroups are indeed normal as well. So the transitivity of the normal relation of subgroups holds when we have a characteristic subgroup, right? We know we have decided, discussed this fact in the previous lecture on silo theorems 1 and group analysis, right? So P is normal in G, right? So if P is normal in G, then this silo subgroup is also unique in G as well, right? Therefore, the unique silo subgroup in H is unique in G as well, right? Okay. What we can actually do out from here is that since we are talking about non-trivial subgroups and H is an arbitrary non-trivial subgroup, now since H is normal in G is an arbitrary non-trivial subgroup of G, and if P is the characteristic silo subgroup of H, then P is also a non-trivial normal subgroup of G. Then P is normal in G is non-trivial. So we can assume H, or we can replace H with any of these P's, right? We can replace H with these characteristic silo subgroups, because since H is an arbitrary non-trivial subgroup, we can assume any existing non-trivial subgroup to be H. We have seen that in this case, when order of H is 6 or 12, then H indeed has a characteristic silo subgroup, which indeed comes out to be normal in G as well. So H can be replaced with these P's. Therefore, we can replace we can replace H with these characteristic silo subgroups if necessary, right? That is, we can consider the order of H, so it can have order 2, 3 or 4, right? Because if order of H is 6, then the silo 2 subgroup will be of order 2 and the silo 3 subgroup will be of order 3. If order of H is 12, then its silo 2 subgroup will be of order 4 and its silo 3 subgroup will be of order 3, right? So the possible orders of the characteristic silo subgroups can either be 2, 3 or 4. Hence, we can replace the order of, if we replace H by any of these characteristic silo subgroups, then order of H is basically 2, 3 or 4 after replacing it. But in all these cases, let G bar denote the quotient group G modulo H. Now, if I replace the H by these characteristic silo C subgroups, characteristic silo P subgroups, in which case the order of H can be 2, 3, or 4, this implies the order of G by Lagrange's theorem. So order of G was 60, right? So 60 by 2 is 30. It can be 30. 60 by 3 is 20, or it can be 50, right? But there is an important observation which comes out from here is that a group of order 30 always has a unique silo 5 subgroup, right? Right? A group of order 20 is precisely of the form, I guess it's of the form p square q, right? 2 square 5. Yeah, it has of the form 2 square 5. And in this case, we know it has a normal silo 5 subgroup again. Right? But then if I consider a group of order 15, then it will have, so we have a group of order 15, right? So yeah, so we have here 2 square q, right? A group of order 20 we are talking about. Is this valid? Yeah, it's valid. So this is of the form pq, and p does not divide q minus 1, where p is 3 and q is 5. So p does not divide q minus 1, right? So if p does not divide q minus 1, then what do we have in this case? What do we have in this case? Is that it has a silo subgroup? Yeah, order of 15, right? So pq, it has a silo subgroup. Yeah. So in all the cases, therefore, in either cases, G bar has a silo 5, unique silo 5, or has a normal subgroup P bar of order 5. See, we should not be talking about uniqueness here, because uniqueness is obviously not obvious. Yeah, right? So G bar has a, because yeah, so correctly, yeah, yeah, 220, yeah, okay, we do not need to talk about uniqueness, right? When we are doing group analysis, I often get confused at some points. I am after all a human being. Whatever, G bar has a silo subgroup of order 5. That's enough. It has a silo subgroup of order 5, say P bar, right? But I'll obviously want to check whether it should be normal or not. um I guess it will be normal. G bar has a unique, has a normal silo subgroup of order 5. See, in case of PQ, it's obvious. In case of a group of order 30, is obvious. In case of a group of order P square Q, I guess it's also obvious. Because we have the group of order 2 square Q, 2 square 5, right? And the order of number of silo 5 subgroups must divide 4. Yeah, it will have a normal, it will have a normal silo 5 subgroup. Yeah, in all the three cases, it will have a normal silo 5 subgroup, right? Right? Yeah, correct. So G bar has a normal silo 5 subgroup. See, it's obvious from the fact that N5 must divide 4, but then the only possibility for N5 is 1. So it will have a unique silo 5 subgroup, correct? So G has a normal silo 5 subgroup of group 5. Let it be P bar. Okay. Let H1 be the complete pre-image, of P bar, and P bar is a is a subgroup of G mod H, that is G bar. So H1 is the, if it's the complete pre-image of P bar, then it must be in G, right? Complete pre-image means pre-image under the natural quotient map. or the natural projection. Pre-image under natural projection. If you recall what's a natural projection is, so if I consider a normal subgroup H of G, then the map G to G mod H such that any element G is sent to G capital H. This is called the natural projection map. So we are taking the pre-image of H1 under this natural projection map. That is called the complete pre-image. But since since P bar is normal in G bar, H1 is evidently normal in G, right? H1 is obviously not equal to G. And what more can we say is that, what can I say about the order of H1? See, order of H1 must be order of P bar times order of H. So it must be order of P bar times order of H. But P bar is a silo 5 subgroup. So this means 5 divides order of H1. But then H1 again comes out to be a non-trivial normal subgroup of G, which has 5 as a factor. But that is not possible, but which is a contradiction. Contradiction to star, right? Contradiction to this, right? Contradiction to this fact. Where did I write it down? Yeah, contradiction to this part, right? That if H is a non-trivial subgroup, then 5 cannot be a factor of it, if you recall, right? Which is a contradiction. Therefore, in any case, we cannot have a non-trivial normal subgroup of G. This implies G is simple, right? Now, this is a very important result. So we can state this as a corollary, that is A5 is simple. Now it has a different proof which is quite complicated, but from this analysis it's quite simple, because A5 has two distinct silo 5 subgroups. Which are given by its two distinct 5 cycles, which are the cycles 1, 2, 3, 4, 5, the cyclic group generated by this 5 cycle, and the cyclic group generated by this 5 cycle, 1, 3, 2, 4, 5. These two are distinct silo 5 subgroups. And if you recall what is the order of A5, so it's the order of S5 by 2, but order of S5 is 120, so it's 60. So A5 is a group of order 60 with more than one silo 5 subgroup. So this should imply A5. Right? We actually have another very important proposition, which is a continuation of this group analysis, but we are not going to talk about that, at least in this lecture. I might be talking about this in some other lecture, so I just write it as a proposition, that is, if G is a simple group of order 60, then G must be isomorphic to A5. Okay. So we end this lecture here. In the next lecture, we are going to start our discussions on direct products of groups, and then we will be entering the concepts of the fundamental theorem of finite abelian groups. So meet you guys in the next lecture.